Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to review together the preparation of the scan plan for phase array inspection of a single V weld in a thin wall axial piece, which can represent seam welds in basically small thickness pipeline. So I'm going to start first by, as always, we're going to start by go to the piece and define our piece. When we click on that, we have an option as a default to choose as a axial piece. And when we choose that, the dialog here will give us parameters that can help us to define our piece. Specifically for this example, I want to choose the OD of the outside diameter of my piece or pipe to be 320 millimeter. And then I want to make it a thin wall, so 6.35 millimeter would be the thickness. And you will notice that when the outside diameter and thickness is set, the inner diameter would be automatically set based on these two values. Next thing would be that there's a sweep here of 100 degree. That basically is a choice that how much of these axial piece we want to show. For instance, I can go to 180 and show more of these, but probably in this case, I can only go 80 degree would be enough to actually show that it is like a curved piece and probably will have enough room for my wedge to sit under. So I'm happy with this selection. Then I go to the weld, and in this case, I don't want to make any much changes to the dimensions. I'm happy with it's a 30 degree bevel, and we have a 2 millimeter by 2 millimeter root. I can turn on the dimensions here so that I can see all the dimensions on the weld. But what I want to do though, I want to add cap here, top cap and bottom cap, and basically change the overlap slightly. And also I want to modify the has to be a smaller to this like a gray area parallel to the weld bevel. So now that I've defined the piece and the weld, the next step would be to add a probe. And here I come and add a phase array probe. The default probe and wedge that we always saw in BeamTool appears here on the piece. But one thing that you will notice is that it already basically pinned to the OD of the piece. So it basically seems like BeamTool already know that you're inspecting a curved piece. The bottom of the wedge seems to be curved, and that's what also you will see here as an option that by default the wedge is pinned to the OD. If you select no pin, it's not basically pinned to the OD, but still the curvature underneath this wedge is matching the curvature of the piece. So obviously in this case we will choose that it should pin to the OD. If we go to the basically details of the probe and wedge, again we have our default probe with 64 element pitch 0.6, and our wedge essentially have the same parameters as the default, but as mentioned here before, now by default the bottom of the piece is matched to the bottom of the wedge is matched to the piece and match the piece. So now here, again, I can make changes to the probe and wedge since it is a thin wall and our weld is a small weld. I'm probably going to choose to use smaller aperture probes. In this case, my choice is 5L32A11 probe from Evident, which is 32 elements, 0.6 pitch, and also I'm going to go and change my wedge to SA11 M55S. And again, you will notice that although now the length is smaller, but the bottom is again curved. Now, at this point, as usual, what would happen next will be to define a beam set. And I want to choose sectorial beam set again. If this was a flat piece, I would basically my train of thought would be that this is a 30-degree bevel, so I want to go somehow between 10 millimeter from the normal, which is 60 degree, is a normal to this bevel. So there's something between 50 to 70 would probably be good. But the first question that come to my mind is that what am I actually specifying here? When we had a flat piece, it was clear to us that any angle that we choose here for refraction angle will be with respect to the bottom of the wedge, as a normal was always normal to the piece was the same as normal to the bottom of the wedge because they were both flat. But here, in fact, what is the angle that is being generated? It is what is the reference of that angle. And that's what you will see a hint here that BeamTool tells you that the beams are being corrected for the curvature of the piece. And some instrument may or may not support this or support it in a different way. And you having an idea of what instrument you want to use, this is an important thing that you need to pay attention. So if I click on the more info, this is where we can read a little bit more information with respect to this axial configuration. In fact, in the axial configuration, we need to do beam correction based on the angle we choose and the curvature of the piece we have. The options for the corrections that you can have would be no correction, full, or partial. And this would be with respect to what is the reference that has been used to generate the angle that we ask BeamTool to basically create. The full correction will be the case that always the reference will be the flat line that is basically flat at the bottom of the wedge, and a normal to this flat face would be the reference. So if you say you want to create a 60-degree beam, what BeamTool gonna do is that it's gonna draw a line to the extent here that would be flat, which actually you see in this image also. And then with respect to normal to that, your angle would be 60 degree. Now, this is a little bit counterintuitive. What can be more intuitive, that is more close to what we expect from Snell's law maybe, is a partial correction, which in this case, the beam that is being generated is with respect to local normal at the surface. So if this is a beam exit point, what happens is we have a normal to the surface, which is essentially a line that goes through along the radius of the OD arc, and then our refraction angle would be respect to that normal. And that's what we, in most cases, we prefer to use. And no correction would basically pretend that this is not a curved piece and do all the refraction with respect to the bottom flat and then just trace the beam into the curve. Now, what is important, obviously, the thing that's important is to make sure that our instrument is aligned with what we want to do. So we need to have information with respect to what is supported in the instrument that you want to choose. If you in that instrument select the angles after you set up your scan plan, which of these scenarios is going to happen? And then you want to make sure that the beam tool matches with this scenario so that you be sure that when you do the inspection, you're actually getting the angle that you plan for. To show this a little bit more clearly, here there's an idea of what happens if you generate let's say 60 degree or same angle linear. If there is on full, means that always your reference would be normal to the flat piece. Obviously, those all going to be parallel beams. But if it's partial, that at every spot, at every beam, we look at the normal to the surface, normal to the OD surface, because the angles to normal would be different, although they're all aimed to create, when you say 60, but 60 with respect to different normals would create different angle beams, in fact, in the piece. And if you just choose no correction, all the angles 60 degrees are with respect to the bottom flat as if this is no curve, and then it's just traced from the into the curve piece and then bounced from the normal to the ID and OD after each bounce. So in this case, if I go to I think the instrument, my default on the beam tool is the correction on full, and for this example, I'm going to change that to partial and save. And you just notice that as I came out of that, my beams slightly changed. Also, the next thing I want to do in my sectorial, I want to use the full aperture. So I just say the full element in my aperture, and here I can choose to display the elements that are generating my beams, which in this case would be all the elements. Now, the next step here would be to make sure that I'm actually covering the bevel. So what I can do is to move my wedge closer. And here, as you noticed before, these are the options, these are the tools that help us to move the probe, and here I can move. But one thing you notice is that now this distance is the distance from the front of the wedge to the weld center along the arc. So you notice that it's not a straight line anymore, it is essentially a arc line. So that's the important thing, and that's kind of like the way that the choice here is that to make it easy for inspection, because typically when you have a curved piece, it was very easy that you have like a magnetic ruler or something that you can easily mark along the curvature. So I can move this closer and closer until my beams essentially start to cover the weld. And if we have the information about the size of the cap, that can tell us how close we can get to the weld. And here in this case, it seems to be like a good coverage. I'll have some redundant angles at the beginning that I can cut so that I can just cover the edge of my has, and on the other side I can increase my largest angle slightly to make sure I hit the opposite side has and on the root side. But another important thing to note here is we talked about how these beams are being generated based on our choice when they come to the curved interface when they want to enter the piece. But we notice that they are also going to be reflected back from the inner diameter or the basically back wall, which again, each of these points would basically have different normal as they are being on different location on the curve. So it's not really intuitive that what we actually get after reflection. What can help us though here is the beam highlighting tool that specify all the information about the beam. So here, particularly the information that's important or useful is the angle of intersection with the bevel. Our goal here was that we inspect this bevel with the angles that are roughly within, let's say, 10 millimeter of the normal. So we ideally want to hit this bevel 90 degree at all location, but obviously that's not going to happen. But we want to be somewhere between 90 and 80. And we already know that our beams are probably not exactly what we generated. We know that based on the option we chose to be 54 and 71 based on the normal to the curve. But after the skip, we really don't have any idea that what is the final angle that hit the bevel. But this beam highlighting tool and this information is going to be helpful here. For instance, for the highlighted beam, it shows that the angle of incident, what actually hit the bevel, is 86.16, which is really good. To just confirm that, actually, what I can do, I can come to one of these tools in the CAD tool and use the angle tool and go on the image and try to actually measure this angle roughly. Put the angle tool, and I try to put one leg on the bevel, and what I read is the angle that matches the intersection angle. And now if I keep moving this to the different ones, you keep seeing that I'll have different angles. And as I move this through, for the last beam that cover, I'm still within 80-degree intersection, which is 10 degree from the normal. So that told me that my I'm covering the bevels with the correct angles. Now, the next thing to notice here is that I may be tempted to now increase this inspection to the third leg with the logic that now the same beams, after they basically skip from the OD, they can also cover the bevel on the opposite side. And generally, this is something that people may tend to do. But one thing that is important to notice here is that when we have a cap, and especially a large cap, uh, these beams will interact with the cap and they will be really not reliable after a skip. There is a tool in BeamTool to actually show that. And if you come to the weld and choose the option to project the beams into the cap, then what happens is that your beam tool acknowledge that the sound can propagate into the cap also. So here, if we go to the first leg, we see that some of our beams go to the bottom cap. And if you go to the second leg, obviously the beams that go through the first go through the bevel, but then after they hit the cap, they again will be reflected through the curvature of the cap. And then we will not have angles that we thought we will to cover the bevel on the opposite side. So then that will hint us that this should be a two-sided inspection. So here, I'll just turn that off. Now, the last point I want to make here now would be with respect to, this is the technique that we designed, but how we also translate the information of the wedge into the instrument that we have. Typically, it was easy because when it was flat, it was very clear that what is the height of the first element with respect to. It would be with respect to the bottom of the wedge, or what was the height with respect to was pretty clear. But here, since there is a curve, the question would be, what is this height is defined with respect to? And that is, again, another thing that is different in different instruments. Sometimes in different instruments, when you choose an axial piece, by default, they want you to define the height of first element as a distance from the first element to the normal to the flat portion, or sometimes they wanted to show it with respect to the surface. Let's look into that in terms of it use a single beam set. Here, for instance, if I just set this to 0, here what they may need is distances or this whole distance. So for BeamTool to provide both options for you, what you can do is to come here on this side, and from this menu you can choose a create wedge drawing. When you click create wedge drawing, as I say, the wedge that you have and use, the cat drawing and dimensions all gonna be here. And one thing you notice now is that the Z, or the height of the first element in BeamTool, what you saw in the dialog before, is from the first element to the flat extent of this piece the way it's drawn. But some instruments will ask you to add basically that distance with respect to the bottom curve. And that's why you can use the SCAD tools to actually measure this distance. And now you would notice that because of the curve, that would be 16.95. So basically it's slightly larger, or the height is with respect to bottom of the curve. So this tool here then would be helpful for you to make sure that when you define your wedge in the piece, in your instrument, you make sure that you're actually having a correct piece, same as what you designed your scan plan for. In the next videos, we'll go through the different pieces. Thank you.